All right. So, hi, I'm Doug. You can just call me Dougo. Forget that whole last name business. So, I've been a network protocol engineer for a long time. In the networking world, we have very mature products for helping, or tools for helping us do our job. My favorite is Wireshark. So, in this presentation, I'm going to run through what is Wireshark. I'm going to explain what support exists today for using Wireshark on Lustre and Elnet, and just run through some basic uses of Wireshark for those who may not have the chance to have used it yet. So what is Wireshark? Wireshark is an open source GUI-based application for doing protocol analysis. You can get Wireshark for Windows, for Mac, and of course for Linux. As a protocol analyzer, it allows you to capture packets as they come across a network interface. It's taking a copy of the packets going in and out of a network interface. It allows you to save them in a format called PCAP, which is a binary packet capture format. It allows you to filter on these captured packets to look at the protocol headers and isolate just the ones that you're interested in. It also gives you some ability to do some statistical analysis over the set of packets that you've captured. So, in that it uses the PCAP format, there's a library in Linux that I think all distributions ship with today called libpcap, and this is used by Wireshark. It's also used by the command line tools for packet capture such as TCP dump. This is very handy because it means you can capture packets using a command line tool on your target such as TCP dump, copy the PCAP file to your own PC, and then open up Wireshark to do sort of a post-analysis of what you've captured. Or you can attach the PCAP file to a Jira ticket to give us a little more information on debugging problems. Wireshark is extensible through something called plugins, or they call dissectors. A dissector is an entity which allows you to decode a new protocol. So you're adding new protocol support to Wireshark as a plugin. Dissector has to do two things. It has to give Wireshark a fingerprint of how to identify your protocol within a packet by whatever means you can find. And once that is found, you have to provide callbacks to Wireshark on how to decode the individual fields of your protocol. So myself, I use Wireshark for three predominant things. One is to debug problems. So if I can reproduce a networking-based problem while I'm running packet capture, I can then do post-analysis to give me more exposure to what's going on beyond, say, logs or just the code itself. The second use is white box testing. If I make a change to a protocol in terms of the fields or in terms of the sequence of packets, I like to use Wireshark to find out that my change takes place when I want it to take place and doesn't take place when I don't want it to take place. So it gives me good exposure. The third one, which might be a bit applicable to Lustre, is if you're lacking in documentation about the protocols. For example, you don't have a protocol map that explains all the fields and what they can be set to. If you have a dissector for, a supported dissector for your protocol, you can do some packet captures, and then you have an interactive tool for looking at the protocol and coming up with a better understanding of it, which is great for someone who's learning because they can do different operations, capture packets, and then in the comfort of their easy chair, walk through the packets and figure out just how this product works at a protocol level. So I wouldn't say it replaces documentation, but in lieu of documentation, it's the next best thing. So I guess the question is it supported today for Lustre and Elnet, i.e. do we have dissectors? And I'm happy to say we do. We've actually had some for quite some time in the Lustre contrib directory. It looks like a while back the engineers at Bull, I believe it was, created the first pass at these dissectors. I believe they did it back in the 1.6.x time frame of Lustre, so they're a bit out of date. I think they were a work in progress because there was various problems with them, and they weren't up to date with the latest Wireshark plugin APIs. So with a desire to start using Wireshark on Lustre, we've updated these dissectors so that they now use the latest plugin APIs for Wireshark. We've also updated them to be able to decode the 2.4 Elnet and Lustre headers. And I've added in a new feature to it that they now are able to decode Lustre and Elnet packets within an InfiniBand frame. So for anybody who thinks that Wireshark can only work with TCP and Ethernet, that's not true anymore. It actually has the power to decode InfiniBand, but it can't capture it. And in a bit I'll explain to you how you can capture your InfiniBand packets. So to build the dissectors so you can use them, you first need the Wireshark headers, and you can get those through a package manager by just getting Wireshark devel. However, when I tried this with CentOS 6.3, it came back with the 1.2.8 version of Wireshark, and this is way too old for our dissectors. So what I tend to do is just go and get the source and build it for myself. The current stable version is 1.8.6. If you get that, you also need the GTK2 devel and libpcap devel libraries. You do the usual config, make, install. You end up with Wireshark in your user local bin directory. You will also have a library out there where dissectors need to go. Once you've done that, on that system, go into our source tree, 2.4 version and up, and go to the Lustre contrib Wireshark directory. If you didn't use the package manager, you do need to edit the make file to tell it where you have your Wireshark source tree and what version you're building for. Do a make install, and that should put the dissectors, after they've been built, into the appropriate location for Wireshark to be able to find them. To verify that, when you run Wireshark, go under the help menu and choose About Wireshark and click on the plugin tab. Scan through the list of plugins, and you're looking for Lustre.so and Elnet.so. If they're there, you're good to go. So capturing packets with Wireshark, you just go under the Capture pop-down menu and choose Interfaces. You'll get this pop-up window, which is hard to read, but it's showing you all the interfaces that's found on your box. Check off the ones you want to capture on, click the Start button. Do whatever it is you're going to do, click the Stop button, you now have a series of packets captured. The problem with Wireshark is it tends to be very resource intensive as it's capturing. It likes to play with the GUI and do different things. So I would recommend definitely using the command line tools like TCP dump to capture on your target, and then copy your PCAP file off to your PC where you can use Wireshark happily to decode it. So for InfiniBand, Mellanox has created a tool called IBDump, which is a parallel to TCP dump. It gives you the power to capture InfiniBand frames from the Mellanox driver on the system that you run it on. I give the rather long link of where you can find that, or you can just simply Google IBDump. It's not a very common term. They supply RPMs for various Linux distributions, so find the right one for you, install it. You run it like TCP dump. It stores everything in PCAP format so that you can then bring that file over and use Wireshark to decode the packets. Once you've opened up a PCAP file in Wireshark, you'll get a window similar to this. Again, very hard to read, unfortunately. I've highlighted in red blocks different zones I'm going to walk through. The top one just has pop-down menus and icons, but it has a field in there called a filter field. I'll be explaining that in a little bit more detail, but that is critical. If you don't know how to use the filter field, Wireshark is useless to you. The next zone is the list of packets that we're currently seeing in the PCAP file. There is which you can't see, but there is source and destination columns in there, which normally would be populated with IP addresses. But if you set up an Etsy host file for yourself that maps your IP addresses to proper names and turn on name resolution in the Wireshark preferences, you get nice readable source and destinations to make it a little bit easier to figure out what you're looking at. The next zone is a breakdown of the currently selected packet from the packet list. This shows the protocol headers from outermost protocol to innermost protocol header. Each of these has a little arrow next to it that you can click on to expand it to show you the fields in human readable format for that particular protocol. The next field is a zone is a hexadecimal dump of the packet, and then finally just a status line. So if you capture InfiniBand, there's just a couple differences here. One is that the source and destination fields aren't IP addresses, if you're using RDMA as we do. It comes back with the LID numbers. And when you go down to the breakout of the protocols for a given packet, the Elnet and Lustre protocols are within the InfiniBand frame, so you have to expand the InfiniBand protocol to be able to see those, so don't miss that. So filtering packets, the most basic way to filter is simply to go to the filter field and type in the name of a protocol, like TCP, IP, Elnet, or Lustre, and hit return, and the display list will update to show you all the packets that have that protocol somewhere in their protocol list. You can do more advanced things with the filter field by typing in the name of a protocol, dot the name of a field within that protocol, and then an expression like equal to a value, greater than a value, less than a value, what have you. You can also do and ors. It uses a very C-like syntax for doing filtering. The field is a sort of an interesting field in that as you're typing, it turns red until it understands what you've typed, and then it turns green. So it kind of tells you up front whether you're making spelling mistakes or not. One thing that I just do as a little bit of a hint, there is a time column in the packet list that shows you by default the number of seconds and subseconds that the packet came in since you started the packet capture operation. I don't find that particularly useful, but if you go in the View pop-down menu, you can change it to a different option. And the one I prefer to use is the number of seconds and subseconds since the previous displayed packet, i.e. the packets we're filtering on. This is useful because you can, for example, filter on Lustre once you've made this change, see all the request responses, look at the response packets, and the number of time next to it is basically how long it's been since the request went out to when you got the response back. So you can sort of get the time that it's taking for these requests to be processed. So here's just, which again is hard to read, but this is what the LNet header looks like when you expand it. It shows you in human readable format all the fields in nice laid out format. If a field can be broken down into further subcomponents such as a NID, you can expand those and get a good look at those as well. And the Lustre header obviously works the same way, and you have things like the whole portal RPC header is one big block within that. Now, these aren't just textual fields that you can look at. You can also interact with them. One of the things you can do is click on it, such as I've clicked on the message type field for LNet here. And if you look down to the hexadecimal dump, it will highlight the bytes that were used to decode that field. This provides you with more information. Like, for example, here I'd like to know whether the message type is 64-bit or 32-bit, or if it's big endian or little endian. By clicking on it and looking down to hexadecimal, that provides me with that feedback, which interestingly enough shows that we're host byte order with a Lustre today, not network byte order. At the bottom, the status line shows you in brackets what the known name for that field is. So in this case, it's lnet.msg_type. So that now tells me what I can type into the filter field if I want to filter on that field. So I can just type in as a filter lnet.msg_type = 1, and then all of a sudden I'll see all of the LNet put packets in my list. Being lazy, the Wireshark people have given us another way to do this to minimize typing. If you right-click on a field, in the pop-up there is an Apply as Filter option. This allows you to take an existing field and make that your filter. So in this case, I've clicked on a destination NID field. So if I choose that as my filter, it'll update the filter field to say, show me all the packets whose destination NID is this particular NID. That can be useful for things like in Lustre if you want to see all of the operations on a given FID. So you can find a FID in one of the packets, right-click on it and say, filter on this. All the packets will then be updated to show you only the ones that are acting on that particular FID. So like I said, this is where the power of filtering really comes into play. So now, in terms of statistical analysis, there's not a lot that's useful to Lustre and LNet within Wireshark. It was really set up for things like ACTP and the usual protocols that people are using. So I'm just going to quickly run through just a few that I find might be useful. These are all under the statistics pop-down menu within Wireshark. The protocol hierarchy window just breaks down all of the different protocols in the currently filtered packet set to show you what percentage of them go to different protocols. Now, if you're running InfiniBand and you're only using it for Lustre and LNet, hopefully that's all you're going to see. But this is an interesting window to verify that you don't have other traffic on your network that's taking up bandwidth. The packet length shows you your distribution of packets based on their size. So it gives you a feeling of whether you've got a lot of big packets, a lot of small packets, how efficient you're being. The flow graph should be useful, but currently it isn't. Unfortunately, the code goes down to the LNet header and stops. It doesn't go to Lustre for some reason. And LNet just simply says, well, I'm an LNet put or an LNet ACK, and that's all it's telling you. So that's pretty useless. However, I have found that with one-line code change in Wireshark, you can turn this into this, which does go down to the Lustre level and gives you a more broken out detail of your flow. So hopefully, I'll look into being able to push this upstream with maybe a preference option to control it. And then we'll be able to do this more often. And so this is a great way to go through and verify your sequences of your RPCs to make sure that what's happening is really happening. Finally, the one that's tends to be useful, and I think we will find some use of it over time, is the I/O graph. This gives you the ability to graph numerical information about your packet stream. So in this example, what I've done is created two graphs that overlay each other. One is a line graph that shows the packet rates for LNet. So I filtered on LNet and made it a line graph. And the other one, I'm filtering on, well, what is essentially ping packets. So I'm looking into the Portal RPC header, and I'm looking at the PBOPC field and comparing it to the number 400. 400 is a ping packet. So effectively what I've got there is the little red bars representing when the pings occur and how many ping packets there are, overlaid over my overall packet rate for LNet. And finally, sort of one little advanced item the I/O graph has is if you go to the unit pop-up for the y-axis and change it to advanced, you get this whole section in the middle appearing called calc. This allows you to do calculations on numerical fields in your protocol header. So you can filter out a set of packets, and then you can tell it to do like a min, max, or an average of a particular field that's numeric, and then it graphs that out over time. So that can help you in some useful ways. So that's basically that. I just have one final request, if I might, of everybody. If you're changing protocols after 2.4, please remember these dissectors exist. They're up to date currently, so if you can keep them up to date so this tool continues to be useful, it would be appreciated that you update the dissector in your patch. And that's basically it for me.
Cool. We got time for a couple.
What's the recommended capture length for TCP dump to get this information? Is there an equivalent in IB dump?
For TCP?
For TCP dump, what's the recommended packet capture length to make sure you catch the
snap length, you mean?
Yeah, this, right.
Well, assuming that everybody maintains an MTU of 1500, that would be...
Oh, so grab the whole packet.
Yeah.
Okay.
Because the default is like 200, so you do need
small,
to change
yeah.
it. It is really small, yeah. IB dump doesn't do that to you. It captures the whole thing.
Anybody else?
Cool.
Doug, thanks a lot. That was
Thank
cool.
you.